Okay, so let's come to how to use this self-attention to define an encoder. We mentioned before already how to define this z, these embedding vectors based on the input x, right? Actually, in the applications, we can also have multiple head or multiple copies of this kind of mechanisms. We name this one as multi-head attention mechanism. It is very similar to the multi-channel used in the CEM. So in the CEM, we mentioned that we can have multiple channels, right? Each one we have defined one template, and we can learn different representation for different channels, and which can be further integrated together. Then we can have a more comprehensive knowledge of from the inputs, right? It will be very similar here. Given the inputs like X matrix, we can also define multiple head attentions. So by different parameters, this W, right? We can define different copies of this Q, this result, right? This vector or this matrix as shown here. So we have two copies of this Q, this result. We have Q0, K0, V0, Q1, K1, V1. Therefore, the attention head number 0 and attention head number 1 as shown here. Then they will define a two head attention mechanism with two copies, right, of this QKV, these matrices. So by utilizing this multiple head, this attention mechanism, we can capture more information from the inputs, which can provide a more comprehensive, also more complementary information from the inputs. Okay, so in the application, actually besides two heads, we can have multiple heads. In this page, we show you, we can have like 8 heads. Given the input X, we can define 8 different heads of the attention mechanism. Each one of them can learn one copy of this Z matrix, right, covering all the embedding vectors of the inputs. So we have head number 0 until head number 7. Each one of them will learn one embedding result, like the matrix Z0 until the matrix Z7 as shown here. So we have multiple copies. Then the next question will be how can we integrate them together? We try to integrate them together by appending them to each other or concatenating them to each other. We have Z0 here, and we also have Z1, which will be concatenated to the end of the Z0, and so forth. So by concatenating all the representation learned by different head of the attention, then we can have more comprehensive information for the inputs, right? We have two inputs as shown here by the X. Then we can learn them with more comprehensive embedding vectors by this row, these two rows, right? This row is for the first input, and the second row will be for the second input, right? However, compared with the input, this one will be too known, right? Because by concatenating them together, we have a very known vector, embedding vector for the inputs, and we try to further compress them into more concise embedding vectors instead. And the way we do the compression is by times this result with one variable matrix again. We define one variable matrix WO denoting the output. So by times this embedding matrix with this variable matrix, we can define the final result for the inputs to be Z matrix as shown here. We compress all the entries in the rows into a row with only 4 entries as shown here, right? In this way, we can learn the final output for the input X as shown here by the Z matrix, right? So you can see in the calculation process, we utilize this self-attention to learn different copies of the Z matrix as shown by this one, and we can further combine them together to learn the comprehensive embedding vector like Z as shown here at the bottom, right? Okay, so this is the way we can define an encoder for the transformer. We mentioned we define, given the raw input X, we can define its corresponding Z as the embedding vector, right? So this one will receive this raw text as the inputs. However, we mentioned we have a multi-layer of encoders, and for the encoder which are at the top layer, then the inputs will be some embedding vector from lower layers, right? So besides X as the raw text inputs, we also define this R as like a result from the lower layers as the input instead. So based on either this raw inputs X or based on some like embedding vector from the lower layers R, we can define this corresponding output to be Z vector, right? In this way, we can define the encoder. Given the inputs, we can define its corresponding outputs to be the Z as shown here, right? So this is the way we can define the encoder for the transformer. And in the next page, we will show how to utilize this kind of encoder to define this transform model and how to utilize it to learn some do the translation between different languages.